first talk will be data assimilation, big data and exascale computing. And our speaker is Professor Takamasa from the the university from Japan, and I think you remember, and he gave the talk, wonderful talk on the day 2 on the Assimilation computer. And today is our pleasure to have him here again and give the talk. And we are looking forward to that. Thank you very much for joining us. And Professor Takamasa, please.
Okay, thank you very much. And thank you very much again for the opportunity for the lecture, the second lecture from me. So this lecture is about big data and exascale computing. I would like to start with a 2-minute movie, but I'm not sure if the sound works properly. So if it doesn't work, I will skip. I will share with you the YouTube link. So let me know if you don't hear the voice. I'm now playing it. Do you hear?
Yes.
Okay, great.
Research team. Data assimilation makes it possible to predict sudden downpours, a goal once considered unfeasible. Data simulation enables more accurate predictions by combining data from supercomputer simulations with actual observation data. Let's take a look at sudden downpours. A comparison found major differences between simulation data for sudden local downpours and the actual observation data. Rapidly feeding big data into a supercomputer using data assimilation has made more accurate predictions possible. Miyoshi's data assimilation research team has brought about a weather forecasting revolution. Research on how to use data assimilation in various other fields has already begun. Efficient use of renewable energy. Research to explore the mysteries of life itself. Improving production efficiency and product quality. Infrastructure control, like preventing traffic jams. Better understanding the global environment to live in harmony with nature. Through these and more, data assimilation will only become more important over time. Data assimilation links reality and simulations. Data assimilation links various research fields.
Okay, so this is like a summary of today's lecture, and so I showed this again, in my previous lecture, but just in case, because independent lecture, I assume that some people might attend some lectures independently. So I'm leading the data simulation research team at Riken Center for Computational Science, where we have the flagship, the largest supercomputer in Japan. It was ranked #1 supercomputer in the world until recently, but now it's ranked #2. So we have basically the world's top class supercomputer, and my job is to use this supercomputer for studying the next generation or the future systems, basically. And I have other responsibilities, but I will skip. And this time I would like to go over my background. So I graduated from Kyoto University and I got a bachelor's degree, and I started working for the Japanese government at the weather service. So JMA stands for the Japan Meteorological Agency. That's a national weather service in Japan. And so my career of data simulation started when I moved to the numerical weather prediction division in JMA. So that was like 2002, I think. So it's exactly 20 years ago. So I have like 20 years of experience of data assimilation. And then I had a chance, because I had only a bachelor's degree, I had a chance to study at the University of Maryland graduate school. So this was part of the Japanese government's training, well, the training program for employees, young employees. And that allowed me only 2 years. So that was very strict 2-year period that I had from the Japanese government to study at the University of Maryland with Professor Eugenia Kalney. She was a leading scientist in this field of ensemble Kalman filter. So at that time, at the University of Maryland, there were a group of scientists developing what's called local ensemble Kalman filter, LEKF at that time, and later it was improved to be the LETKF, that's the local ensemble transform Kalman filter. In my previous lecture, I introduced the ETKF equations, the transform matrix, and the local is the domain localization. I didn't have much time at that time. This LETKF is now kind of standard method in numerical weather prediction. So I had 2 years to finish the master's degree, but I was fortunate enough, and I worked hard, of course, to complete the PhD as well in that 2-year period. My PhD thesis was about the ensemble, the LETKF. Well, yeah, I think that at the time already the LETKF, and compared with the 3D bar with the speedy model, that's an intermediate complexity atmospheric general circulation model. And then I moved back to Japan at the weather service. I developed operational model. With the operational weather model, I developed the LETKF, and it took a while after I quit the JMA. But now the LETKF that I started developing at that time is used in operations in the Japanese weather service. And so I decided to move to the academia, because I would like to do more academic research. And so I got a position of research assistant professor at the beginning, and later I had a tenure track assistant professor appointment at the University of Maryland. And about 10 years ago, I decided to move to RIKEN. RIKEN is an academic research institute for all science in Japan. This is considered to be the top institute in Japan, a science institute in Japan, mainly run by the government funding. So it's part of the government, and the Japanese government National Research Institute. So we had a flagship supercomputer, mainly funded by the Japanese government. So I will skip this. So what we did, so this is a highlight from the last year, in 2021, July. We had Tokyo Olympic and Paralympic Games in Tokyo. And at that time, we did a real-time weather prediction. So this is a web page of our weather.riken.jp. We use the largest supercomputer called Fugaku to make the prediction like this. So you can see that this is a time. Every 30 seconds, we get an update. So every 30 seconds, we get the data and that update. You have never heard of it, because this is the only system that we can update every 30 seconds. So we did a real-time experiment in 2021. during the Olympic and Paralympic period. So we actually did 2020 when we didn't have this Fugaku, that's this large supercomputer, was under development in 2020. But the Tokyo Olympics were, of course, at first planned in 2020. So we aimed to do this experiment during the Olympic period. So we identified a suitable supercomputer, Oak Forest Pax, that is a university computer, University of Tsukuba and University of Tokyo jointly operated this supercomputer. This supercomputer retired recently in March, so it's no longer exists, but this was very powerful supercomputer. So in 2020, we ran 50 ensemble members LETKF, but with the Fugaku, we improved the ensemble size to 1,000. Of course, it's better to have more ensemble members in the ensemble common filter. And we could also afford running 10 ensemble members for the extended forecast. And we also made some changes. So we used the Fugaku about 9%, that has about 500,000 cores. So this is really massively parallel computing. And any supercomputer at this time is massively parallel. So the LETKF, it's suitable for that. And we were allowed to use this much Fugaku nodes exclusively to make that kind of forecast. First, I would like to show some examples of the forecast at that time. So the left side is the forecast, and the right side is the observation. So that's supposed to be the verification truth. So if you look at this prediction, this is, by the way, Tokyo Prefecture, and this is the center of Tokyo. And this is north of Tokyo. And we had rain system here, the main rain system here. And this is what I was observed. So this is moving, so I will stop it. So this is the initial time, 7:20 Japanese time. And the forecast and observations are almost exactly the same, because this observation was assimilated by the LETKF into this forecast. So this is the analysis at times, 7:20 p.m. And actually, this is quite difficult. I believe that no operational weather prediction system can do this like this. If you observe like this, this one, this is a distance like 0.2 degrees longitude. So it's like 20 kilometers or less here. So the system here is very small. So this is really precise representation of this observation. The model resolution, we chose 500 meters. So we resolved up to 500 meters. This is quite accurate if you compare with the observation. So 10 minutes, we can see that this here is developing, so that the blue became red. Red is quite heavy rain. And the observation also shows the development of this rain system. So in 10 minutes period, this convective system developed like this, and that's really hard to predict usually. We were very successful to do that. But if you look at this thing here, this is another heavy rainfall, but a very small scale. And it didn't exist at the initial time. In 10 minutes, it appeared like this. And we have nothing like that in the prediction. So if you have basically no observation, it's really difficult to predict this type of event. And in 30 minutes, so this thing became like that, and this is completely missing. But this part is pretty well predicted. So there are good things and also something that we need to improve. But in well, this is the first time that we really could predict this type of very small scale convection, individual convection very precisely. So this is quite an achievement using Fugaku. So this is another case that I showed at the beginning in a movie. So this is 3:30 p.m. in the local time, July 30th. So this is during the Olympic period, and this is a heavy rain in the center of Tokyo. So there must be a lot of Olympic Games happening in Tokyo, and it might have affected some of the games, maybe. I don't know. We could predict like this if it's a single ensemble member, or the deterministic prediction. And we run 10 ensemble members, and we counted the number of ensemble members having heavy rain, defined by this probability of 30 millimeters per hour. So we see that more than 3 members out of 10, that's 30% of the chance, shows the heavy rain here. The 30 millimeters per hour is the orange color here. That's quite a narrow area. And we had some predictability for that. So this is quite promising. So we care about this type of prediction because this happened in Kobe. So by the way, Kobe is where we are. It's about 500 kilometers west of Tokyo. And we had this event in 2008, and 5 people died, unfortunately. So this happened only in 10 minutes. So if you could predict the heavy rain exactly where it occurs 10 minutes in advance, then people could just step up out of the river area, then we could have saved those lives. So that was a strong motivation to develop this type of system. So the idea here was big data assimilation. So we had a powerful supercomputer. So this is a previous generation K computer, and new sensors to combine. So new sensors produce like 100 times of more data that I will talk about now. So this is a K. The K computer started in September 12 until August 19. So during this period, so my team started in October 12. So we had a full period to use this computer. So we did a lot of experiments to explore new things. So my colleagues at RIKEN and the University of Tokyo, JAMSTEC in Japan, they developed this global atmospheric model. And this is quite amazing, so that they resolve up to 870 meters of the atmosphere globally. So this is a global 870 meter simulation done in 2012 and published in 2013. And this is still the highest ever resolution global simulation of the atmosphere. So this is, well, so the computer grows rapidly, but still this is the highest resolution global simulation that, well, keeps the record for about 10 years in the next year. So this is quite unusual, and that was very impressive. And this is not the simulation, this is the real data from the new radar technology. So this is also really amazing. So when I saw this for the first time, I was really shocked. So this is noisy, so I will stop the movie. I don't know how. Oh yeah. So this is a phase array weather radar. That's a new type of radar. Usually the normal radar is parabolic antenna, and we have a line to observe. So we need to rotate 360 degrees in the azimuth, and then we also change the angle, the elevation angle, so that we can observe like 15 layers in 5 minutes, something like that. Yeah. But this thing can observe 100 angles immediately. So it takes 30 seconds to rotate 360 degrees. And then we get 100 levels immediately in 30 seconds. So that's why when the parabolic antenna observe a single line, this can observe 100 lines. That's why it produces 100 times more data. So we have observation like 100 times more data, and we have a high resolution simulation. This was a global system, but to do this, we need to have a regional system. But basically, the idea is the same. So we have very high resolution regional system with very high resolution and rapid data. So the data assimilation combines these two, and we could predict or precisely predict this type of convective storm. So we get a sudden heavy rain because the development of the convection is really rapid. But if we can predict like 10 or 20 minutes in advance, then we can prepare for that. So that's the idea. So that's how we started the project in 2013, and it took us a while to develop this system. We first tested this event that happened in September 11th. This is Kobe city downtown here. And we got the rapid development of this heavy rain and hit downtown Kobe. So we ran the system, and this is available at this YouTube. So if you're interested, you could take a look. This is like 2 or 3 minutes movie. I will not play the whole thing, but this is observation. This is what we got by data assimilation, and this is really precise. So if you stop it, this is observation, and this is again what we assimilate this observation. This is produced in the computer, and without assimilating this observation, we have nothing like that, but instead we have something else. So that's why this type of event is really difficult to predict, because only if we have the very rapid update system, we have good predictability. So to make this happen, it took a while. So we started the project in 2013, and it took us like 3 years just to make it happen. But the computation was very slow. We had to spend like 1 hour of the computational time of the K computer just to update the 30-second data. So we need to do the 30-second, less than 30-second computation time to make this for the real-time application. That's why we spent like 4 more years to accelerate the computation and find a good setting, the ensemble size and the resolution of the model and so on to make this happen in real time. So in 2018, another Japanese government project called SIP developed a new type of the phase array radar called MP-PAR. The MP stands for the multi-parameter, meaning the dual pole. Dual pole is a dual polarization. So we have the vertical and horizontal polarization. So we get 2 data from the same cloud with a single radar. And this is 2-dimensional phase array, so that we get 2 separate dual polarization observation. And this is implemented in Saitama University, and that's here. And this is Tokyo. So this can cover many Tokyo Olympic and Paralympic venues. So that's what we use. And the radius of 60 kilometers is the range of the observation from this radar. So that covers a lot of populated area. So we developed a real-time system. So we have the observation from the radar, and that is produced almost immediately after the observation as a file. So the file is produced in this server. We kept monitoring the server and transfer the data immediately once we find a new file on this server. So we developed a dedicated software called JITDT, standing for the just-in-time data transfer. For this data transfer, and it takes about 3 seconds to send the data to here. on Fugaku directly. And then we run the data assimilation system, LETKF, based on the scale. Scale is the name of a regional atmospheric model developed by Riken. My colleagues developed this and optimized for Fugaku. And then this produces 30 minutes prediction. We visualize on the web page that I showed, and also the smartphone app. So we set up these multiple domains. So the outer domain is 1.5 kilometer mesh, and we need to provide the boundary conditions of the outer domain that comes from the 5 kilometer mesh JMA operational system, mesoscale system. So we take the boundary condition at this blue line part from the operational system, and then we run 1.5 kilometer mesh blue domain. And then we have the boundary condition for the inner domain. And this inner domain is at the 500 meter mesh. And every 30 seconds, we get the phased array, MP power observation to assimilate. So we run 1,000 members plus one ensemble mean prediction for 30 seconds, and then assimilate. So that, and also we run extended 30 minutes forecast for 10 members. So that requires about 9,000 nodes of the Fugaku. And 2,000 nodes were used for the outer domain computations. So the outer domain also used 1,000 members, but it's a lot low resolution. So we don't need to spend or use a lot of computations. So the JMA operational system is updated every 3 hours. That's why we have initializing these outer domain every 3 hours by taking the JMA data. And this is how we use the Fugaku nodes in a 24-hour period. And this is an image from the smartphone app. So this is the deterministic prediction. So this is three-dimensional. So we can see the vertical structure of the heavy rain. And also, this is a probabilistic forecast, so that we have 10 members. And if you have heavy rain, more than 2 members showing the heavy rain, then it's a light color. And more than 8 members showing heavy rain, it's the darkest color. So again, so this is the vertical structure. So this is the rain amount. Well, this corresponds to the rain in the sky. So it doesn't mean that it falls to the ground. So, well, this is interesting, but this is what we could do. For every model grid point, we have these values. Usually we don't monitor like this because people care only the rain falling to the ground. But because our system can produce this vertical, the volume, we just plot it like this to see the whole sky. So we succeeded in accelerating our system so that every 30 seconds real time, we could assimilate the data and produce 30-minute prediction in 3 minutes. So this is a forecast lead time at every time of the prediction. So we started our system in 20th of July until the end of the Olympic game. So 9th of August 2021 was the closing ceremony of Olympics. So we completed our computation at the end of the Olympic game. And this is a histogram of the lead time. So most of the time, the prediction, 30-minute prediction was available less than 3 minutes of the process time. So we issued like 47,000 prediction because every 30 seconds we get a new prediction produced. And this is the same plot for the Paralympic period. So this is a different period in August, the end of August to September. Basically the same thing. Most of the time, the prediction was available in 3-minute period. So we did other things as well. So that was what we did with Fugaku for the real-time, very high resolution and rapid update, the rain prediction. But we also explored the big ensemble. So we ran 10,240 ensemble members, the LETKF, and each individual dot corresponds to each ensemble member. So we plotted, actually this shows all 10,240 ensemble. So it's almost impossible to see the individual, but if you just focus on these 16, we can notice that the northern hemisphere are more similar to each other than the southern hemisphere. The waves in the southern hemisphere are more different. Because in this case, we have observed more in the northern hemisphere, less in the southern hemisphere. So it represents, well, so these are equally probable representation of the atmosphere. So we don't know which is true. And these are equally true. So this is interesting. And if we plot the histogram of some variable at some point, then it looks like this. And if we take the subsample of 10,240, so if we assume that this is the best representation, we can see that reducing the sample size, we tend to lose, of course, the resolution of the histogram. And with 80 members, we have 2 peaks, or 160, we have still 2 peaks, but actually this was 3 peaks. So to see the 3 peaks, at least 1,000 members is necessary. And if we look at the non-Gaussian metric by Kullback-Leibler divergence, 10,240 shows like this. So we have only occasional non-Gaussianity, mainly in the tropics. But if we reduce, we tend to see more and more noise. Because a non-Gaussian metric, well, to capture the non-Gaussianity, you need to have a larger ensemble size. About 1,000 is the time when we start seeing similar structure with 10,240. So it seems that 1,000 is some critical number to resolve these things. So this motivated us to run 1,000 members rather than 10,000. 10,000 usually too expensive. So by running 10,000 ensemble members, comparing with 100 members, we can see the covariance structure like this. So from this observation, what kind of impact this observation will produce at this single time step. So this is the analysis increment type of thing from this observation. We see this, like the large scale structure. We usually don't consider it by localization. All of the signals were killed. With 100 members, we have a lot of noise, so the localization makes sense. But 10,000 members, these are significant signals, so that we shouldn't localize and eliminate. So we just computed how much impact we will have by this type of long-range correlations. So just ignoring all the other lines, just focus on the black and red. Red is the 10,240 members without localization. And this is the 80 members. We tune the localization. Without localization, 80 members doesn't work. So you need to tune the localization scale, and this is the best result. So this is a root mean scalar. So the analysis root mean scalar is here, quite different. And we run the forecast. So the root mean scalar grows exponentially in forecast. And this is the 1-day forecast error for the 80 members. It's equal to the five-day forecast error without localization. So this is an idealized experiment, but this is a potential that we could still improve the prediction. So the 1-day forecast error of 80 members may be equal to 5-day forecast error without localization by running a large ensemble. So this is a lot of improvement of the numerical weather prediction. So this type of thing is what we explored with this large supercomputer. This is not exascale yet because it was built in 2012. It was 10 petaflops supercomputer, and we explored the combination of big data and big simulations. So we ran basically 2 orders of magnitude bigger ensemble or rapid update compared with like hourly update is 120 times more rapid. And resolution wise, we run 100-meter mesh, but it's 100 times more mesh numbers compared with 1 kilometer mesh. That's still quite a high resolution in numerical weather prediction, but 100-meter mesh is 100 times more. So this, with this, we explored what will be the choice for future numerical weather prediction. And other things that we explored. So this is the computation using the Fugaku. Fugaku is 100, well, basically 100 times more powerful computer than the previous generation K. And so we explored a virtual observing network. So we have a method of an observing system simulation experiment called OSSI to evaluate the value of observations without having it in the real world. So we have only very few phase array radars at this moment. The INPE we have only 1 at this moment. So this doesn't exist. But we just assume that we have, what if we had this many phase array radars, and this caused a severe disaster in 2020. And we did some experiments, simulation experiments, simulated observations, and then we could improve the prediction of the heavy rain at the critical location for the disaster. So this type of data were very useful in the early, short range prediction, but once we predict longer, since the whole system in the large scale forcing, in this case, the front system that has like several hundred to like 2,000 kilometer scale, they come from the boundary conditions. And even if we assimilate the detailed data inside, everything is wiped out from the boundary. So this has a significant skill up to like 2 to 3 hour period. And beyond 3 hour prediction, there were no skill gained by that many radars. So that was what we found, and it's reasonable because we observe only the local phenomena, and we cannot fix the large scale phenomena. So this is still an open question how we can combine the multi-scale, also different scales together. That's a grand challenge for the atmospheric data assimilation. And another new sensor that doesn't exist at this moment is a phase array in the geostationary orbit. We already have phase array weather radar on board a satellite. So this satellite TRIM already died in 2015, but we had the next generation GPM launched in 2014 and still observing. And these are low Earth orbiting satellites. That means that the revisiting period is quite low. On average, I think once a day we have the radar coverage. So the radar observes the raindrops in the clouds, and the cloud system evolve more rapidly than one day. So that means that one day revisiting period is, well, we cannot observe the same cloud again. So for the 4-dimensional data assimilation concept, we need to observe the same cloud again and again. Otherwise, we lose all the previous observation information. Those things are chaotic. So we have a forgetting factor from the chaos. So it is quite difficult to use this type of information in data assimilation. That's why we explored the geostationary orbit, where we can observe the same location again and again, like every 10 minutes, for example. The geostationary satellite observes the infrared radiances. So this observes the radar. So the radar takes a little longer time. So every 10 minutes is quite challenging, but still at least every hour we can observe the same cloud, or every 30 minutes maybe we can observe the same cloud. So that's this thing, 30 meters by 30 meters phase array. By the way, this phase array here is 2 meters square, and the one that I showed in the previous experiments were like 2 meters square. So 30 meters square phase array is quite big, and still a big challenge to build this big thing in the geostationary orbit. Well, it's very far in space, and we cannot go fix it if there is some problem. So it's really challenging task. But still, we try to see what's the value of having this radar. So we produce a nature run that's supposed to be the truth, and then we observe this nature run by that 30 meter square radar antenna in the geostationary orbit. Then we could observe like this. The 30 meter square radar antenna in the geostationary orbit have a footprint of 20 kilometers. So this is a 20-kilometer footprint. And if we observe what the geostationary orbit is on the equator, so this is like 18 degrees north. So it's not on the equator. Then we have a tilted angle from the equator to see these clouds. So that's how, well, that's even more difficult to observe. So we consider all of those details to produce this simulated observations. And this is the case when we apply oversampling technique. The oversampling, we still have 20-kilometer footprint, but we have the overlapping footprints. So although we have 20-kilometer footprint, we sample 5 kilometers apart. That means that we sample some points, and the next point, if we sample 20 kilometers away, then it appears like this, and there's no overlapping samples. So that's the no oversampling. But if we have overlapping samples, then this is called oversampling. Then we can clearly see more detailed structure with oversampling, even if the footprint size is the same. If we look at the vertical structure, this is the nature run of the typhoon. And this is the case without oversampling. And if we do the oversampling, we can see more near the bottom. So this is where we had the heaviest rain and more structure. So this is quite useful to see this. And we assimilated this oversampling data. We also did the no oversampling case, but that was not very successful. So I just show only the case with oversampling data. So this is the results from 18-hour forecast by assimilating this oversampling data. And this is the case without assimilating this geostationary precipitation radar. And this is a nature run, ground truth. So we had heavy, well, high winds, more than 54 meters per second. That's really a high wind. And sorry. And this was well predicted once we assimilated this GPR. This shows just the potential of having this type of the satellite. So these satellites are really high cost to develop and launch. So this type of experiments are much, much cheaper than developing satellite itself. It makes sense to do this type of designing phase of the OSI. So this is a general concept of what we have been doing. So we developed the big data assimilation system for for the more innovative numerical weather prediction system, like assimilating the existing phase array radar, and then we improve the forecast and we can validate, and we can use those improved weather prediction system in the real world, and then this can give us a feedback what kind of improvement, the further improvement is more useful for the society and so on. And then we start designing the new data. And if we can make this loop, if we design the data and can really show that this data is really useful, then we actually develop a new satellite or something and get the data. Because of this phase of the RC, we have a system to assimilate the new data. So this step is quite simpler because of this RC phase. So this is something that we should do. We now started a new project called ITER. This is a project of the industry satellite, the commercial weather satellite with a CubeSat. It's a shoebox size platform. So it's like 30 centimeters size. It's really small satellite, having a microwave sounder on board to observe the atmospheric microwave emissions. And if we assimilate these, what happens? So that's our role in this project. So now it's a early designing phase. So once we do data assimilation, it's a really interactive collaboration, so that they have some ideas to design the sensor and satellite orbit. And we test different choices of those developments, and we could suggest what will have a better impact on weather forecasting. So this is the concept that we are now doing. So this is a general picture of what we have been doing. So this is the synchronization between the cyberspace and the real world. So we have the nature in the real world. I intentionally include this type of virus or those because we could do many things beyond just the weather, and the infections or those are also related to the weather, environment conditions, and so on. So it's really a complex system in the real life. And we need to first monitor it by sensors and these phenomena, and then we get these sensor data. And what is important is that we get the sensor data on the cyberspace. So we have a lot of tools or communication systems to make it happen. So that all initiated the development of AI just to do some data-driven type of analysis for prediction or the control or something useful to the society. But we used to do the simulation for the weather prediction, and we apply the data simulation. So this is non-effective, so that we get the sensor data like radar or satellites. And then we assimilate into simulation so that simulation can produce the future prediction. We still don't control the weather, but we can at least control our activity. So if we could include some of these human activities in this system, then we could do something to suggest what kind of decision to make, what will be the optimal actions to reduce the risk from these risk factors from the nature. And so the idea is that once we have the cyber, so some people, or in some area, people say that this is a digital twin. So we have the real phenomena and some computer representation of the real phenomena. That's a digital twin. So the goal is to optimize the situation. of the real life. So that's the control. So the data assimilation is based on the control theory. Control theory also developed in many ways, like the autonomous driving, for example. There are AI-based methods, but also the optimal control theory-based methods as well. They use the ensemble Kalman filter actually for the autonomous driving. So there are many things in common and also mutually beneficial. So that's why I showed the AI and data assimilation at the same time here. And many research is now ongoing to integrate or fuse these two approaches. So that's the general view to this problem. So now in the Japanese government, based on our previous research, the cabinet office of the Japanese government set a goal, moonshot goal number 8 recently. That's weather control, basically. So we control and modify the weather and to avoid the extreme winds and rains. So this is the schematic showing we make these severe phenomena smaller or change the location to avoid the impact to the human society. So that's the basic idea. And this research project aims at 2050. So it's like about 30 years later from now. And I was appointed as a program director for this project, a program actually. So this moonshot goal was set based on our research previously. So this was published recently in NPG letters about the control simulation experiment. I showed the OSI, so this is an extension of OSI. I will describe it a little bit now. So the idea is that we'll take advantage of chaos for control. The chaos implies a limit to predictability, of course. That's why the data simulation is not easy. The data simulation is considered as chaos synchronization, and it's not trivial if chaotic systems synchronize. So, but this implies the effective control. So if we make a small difference, we can cause a big change. So if we think about the weather system, what we can do to perturb the weather system by human power is really, really limited compared with the energy of the atmosphere. So what humans can do is almost negligible difference to the weather system. But the chaos implies that even small difference can grow, but it's unpredictable. So I just draw like this schematically to choose a desired scenario, then we can control. But we cannot do by putting very small perturbation at the initial time to choose, because this is unpredictable, but this is chaos. But if we can track the orbit and select a proper orbit, we can do this. That's the idea. So we have a method of OSSE. I already described there are a lot of methodological studies existing. In the OSSE, we first assume a nature run. So this is a nature. And in OSSE, we know it to simulate the observations. And we have a forecast system blind to the nature run. So the forecast system can know the observations. The observations are not perfect. It's a noisy and partial imperfect representation of the nature run. So that's the design of the RC. So we assume that we use the ensemble common filter here, but it's not necessary. But for simplicity, I just focus on the ensemble common filter. So in this case, we have 4 ensemble members. And if we assimilate this simulated observation here, then we update these 4 ensemble members to be closer to the observation. That's the analysis step. What we do next is just to repeat this so that the ensemble members all stay within a range of the nature run. So this is a successful case of data assimilation. So if we have insufficient data or some imperfections in the system, it may diverge from the nature run, then the RC is not successful. But this is how we evaluate the data assimilation system and the observation data. Okay, so now we modify the RC. So the first step is the same. We analyze and we get the 4 ensemble members like this, but we would like to change the nature to the desired direction. So we can make a forecast like that, and if we analyze here, then it's like RC. But we decide what is the preferable or desired state and what is undesired state. Let's assume that the upper side is undesired and the lower side is desired. So this is our decision, because a control is something that we need to decide what is desired. But once we decide what is desired, we can choose this rather than this. Then we would like to change the nature towards this direction. So to take, well, we would like to change from this side to this side. So we can take the full state difference like this. This may be too large vector. So we rescale to make it very small. And then we apply continuously in time. So that's how we choose the orbit of the nature. So we change the nature now. So this is the most important part of this control simulation experiment, but we named it CSE. So we change the nature. In OC, the nature never changed. And in real life, we also never change the nature. But if you know how to change the nature, we could do. So this is how we did. And then we observe this new nature. So this nature, original nature never happened. So we just don't need it anymore. And we apply this perturbation to the nature, so the nature changed. Then we can observe this new nature to keep track where we are. So this is the prediction. So now we apply these changes to the nature. That's why we observe here. Then the analysis will change like this. And we make the new forecast like that from this analysis. Then we do the same thing again. So we choose the lower side and take the difference from the worst. And then we can change the nature even more. And we could repeat this. So we apply this method to the Lorentz model. The Lorentz model is a very famous model. We have the right side and left side regimes, and it randomly shifts. So we know that with this parameter set, this model behaves chaotically, so that we have not all limits to predictability and sensitivity to the high sensitivity to the initial conditions. So this is a case when we apply the control. The control signal is really small, tiny. We can see that in this control, we assume that the right side is good and going to the left side is bad. So we try to control the system so that everything stays on the right side. And this is a case with a successful control. So if we look at the attractor, because we apply the perturbation every time step, the model equation includes those forcing terms. So that's the attractor change. So this is the original Lorentz attractor. And after applying the control, this is a new attractor. So the shape of the attractor changed But what we tried to do was to constrain the state on the right side only, and that was successful. Although we have some change of the attractor, that may not be preferable. Then if this is not preferable, we need to change our target for control. So, but this is interesting, so that we can change this attractor quite effectively by very, very tiny perturbations. So we did something similar with Lorentz 96 40 variable model. So this is a 1-year equivalent time series of all 40 variables, and we identify the extreme values and try to avoid the extreme values. That's the purpose of the control. So these extreme values, like twice a year event, we try to avoid. So if you run 100 years of this is 1-year equivalent, so 100 years of this, and show the histogram, upload the histogram of all of these values, then it goes from -11 to like 17, and this is about 200 events, so twice a year event, extreme, so more than 14.217, that we count like 200 extreme events in 100 years. Then after applying the control, the histogram completely avoids having these extreme values. So this is 100% successful control. We apply the same methods to a typhoon simulation with a global model. And we tried to reduce the intensity of the typhoon, and this was quite successful. This is a strong typhoon, and we made it weaker. Typhoon was weakened. It is for the localized heavy rain event that happened in 2014, July. Hiroshima had a severe landslides, and many people died from that. So it was really severe event. We simulated that to produce an HRN. So we had a very heavy rain in Hiroshima, and if we apply the control, very small perturbations can reduce the rain amount like this. This is quite a bit of reduction. So if you look at the darkest color, it's more than 200 millimeters of rain, and it is reduced less than 150. So the disaster occurs at the critical point. So if we can reduce this much rain, we could reduce a lot of landslides. So that was the goal of this project. So this is still at a very early stage of the exploration. So we just started this moonshot based on these preliminary investigations, I would say. Okay, so now towers, well, I will finish maybe in 10 minutes. So the last 10 minutes is about the fusion or integration of data assimilation and AI. So we had a K computer, as I said, and this computer was good for the big data assimilation, big simulation, the double precision computations. But machine learning or the AI techniques usually use the reduced precision computations or integer computations, and these computers, CPUs, are not designed for that kind of computation. That's why usually machine learning, we use the GPUs, the graphic processing unit. So the graphic processing is usually integer, something like that. So machine learning takes advantage of that. But moving the data is difficult if you have really big data. So Fugaku was in full operation last year, March. This is capable of both the dual double precision computations or single precision computations, or even reduced half precision that usually machine learning use, or the integer computations. So the idea is that I didn't show this general workflow today because I assume that all of you had lectures about data assimilation. I quickly go over. So this is the initial state, simulation, and simulated states and observations. So we have the observation operator to take the difference, and this is the DA module so that we combine y minus hx, and x is updated to be xa. So we have huge data usually if we have a large supercomputer. The simulation size is huge. And if you run an ensemble and high resolution ensemble, this is really huge. And we usually don't save everything. So because we don't have space to save. And if you'd like to train a machine learning using this data, this on-the-fly learning will be effective. So the thing is that if you have big data from the computations, usually the big data is from computations, not the observations usually. If you have big data from the big computers, we cannot move, or we cannot even save the data. And if we can use those data on the same HPC, we can do that. So that's the idea. Learning means that it's a kind of compression of the information. So we have huge data from the simulation, and learning those data means that we save that information in a reduced format or the reduced form. So the network contains all, well, not all, but information from this huge data. So that's how we save the information. Okay, so in this frame, I wrote some of the things here. These are the ideas how we use the AI within data assimilation workflow. So one example is this fusing the big data assimilation and the machine learning. So we have a nowcasting system with different algorithms, like optical flow is a typical algorithm, but we could also use like this LSTM, that's a long short-term memory, and with the convolutional neural network combined, it's a convolutional LSTM known to be effective for the precipitation nowcasting. So if we give a lot of past time series of images, then this can track the image in time so that it can produce the future time images. So if we apply it for the three-dimensional phase array radar data, then we can produce the volume, three-dimensional dense volume image. So this is a volume image. So it's not a two-dimensional image, but a volume image to produce the future time volume image. We found that this works, but if we combine with the numerical weather prediction, the numerical weather prediction can have the future images from the simulation. Then we can push this time series of future images from the weather simulation. Then we can improve even more of this prediction. So that's the fusion of this. So it's kind of an output for model output statistics, but it's an advanced form of model output statistics. So so this is a comparison of the skill of the rain prediction, 10 minutes period of time. So the weak rain to the heavy rain. And this red dashed is all the combinations. So this is quite improvement compared with other methods. So this track is the optical flow. And LSTM is pure data driven. So this is green. So using the numerical weather prediction, it improves quite a bit. The pure numerical weather prediction is this scale. This is like this line, pink line. So this is not quite as good as, well, the nowcasting at the beginning, but it getting better towards the end of the prediction period. But as you can see, that it's clear improvement. Or the surrogate. So we would like to accelerate the model computation, but if we just learn the model data, it's really difficult. So we try to do some hybrid of the physical statistical model. So we run a low resolution model that still contains some process, and then try to do the super resolution. So this is, well, I will not go into detail, but the idea is just to do the super resolution of the low resolution model. So running the low resolution model is a lot cheaper than running a high resolution model. So this is a computer time. Running the high resolution model takes like this time, and the low resolution model takes this green. And convolutional neural network can do the super resolution. So this is purely data driven. DD represents the data driven, so it's a lot faster. And this is a little slower than this because we run still the low resolution model, a physical model, but we also use the convolutional neural network for super resolution. And this is ideal. So when we run the high resolution model, this is a scale. Higher the better. Anomaly correlation coefficient is a scale. So this light blue is a hybrid. And this red is a purely data driven. So it loses scale quite quickly. And this light blue is still close to running the high resolution model. Of course, it's a little worse, but the computational time is a lot faster. So we would like to do this because our prediction, for example, 30-second update requires the Fugaku. That's the only one computer in Japan, and it's super expensive. So the idea is to use Fugaku to produce the network like this, and we could afford running a lower resolution version of the model. And then we could do the super resolution using the data, offline data of Fugaku. So that's how we compress the information that we use Fugaku offline. That's still expensive, but much cheaper than using Fugaku exclusively real time. So that's the idea. And the observation operator as well. So for satellite data assimilation, we need a radiative transfer model that's complex, but we can replace this with a neural network. So it seems that this is working. And this type of research is ongoing in various places. So the idea was, well, so far use the AI methods in data assimilation, but for the future, we would like to fuse the algorithmic level, the AI and DA, with the HPC. So this, I think, will lead to the new meteorology, what we call the fifth science. What is the fifth science? So this is just our idea. So this is not well accepted yet, but just a proposal. So we have the fourth science as data-centric science, like AI type of data-driven methods. And we have the third science. This is well accepted concept of the computational science. So this is based on the theory. And the first science was experimental. And these are the data-driven part, inductive part, and these are the deductive part. And the idea for the prediction science is to combine these two. So data assimilation combines the data-driven and process-driven approaches like this. So we can use data assimilation as a core technology for the fifth science. So this is a case of ocean environment. So the satellite data have a lot of missing parts, and this is the model simulation, but it doesn't have the details. But if we do the data simulation, we can reproduce these fields. And we could also compute the lake environment using like the satellite color, observing the color we would like to have the model representation of, in this case, blue-green algae bloom. And we also did forest simulation. Each individual tree we can simulate, and the idea is to simulate each individual tree globally. It's almost impossible, but we don't know what exactly each individual tree, but we can see from the satellite what's the leaf area index. We were successful to reproduce this observed satellite leaf area index from this type of individual forest simulation. And another thing is about like this press forming engineering program. And if you make these parts, this prediction program is really essential. This is what we call the prediction science. And this is my last slide to introduce our recent activities at RIKEN to propose this concept of prediction science. And if you are interested in more details, I think this is one of the future potential of data assimilation in beyond meteorology and applying to many different fields. Thank you very much, and that's it from me. And I think that we have some time for answering questions.
Yes, thank you very much, Professor.
Yeah.
And it's, I think there are some number of questions on chat.
Yeah.
The first one is high, vertical resolution you use for global modeling.
Yeah, that's a good question. So the vertical resolution, well, the question is about the vertical height of the global model, right? Well, the height is like 30 kilometers in that case. We have different versions of the model, but for running a very high resolution global simulation, we didn't increase the resolution vertically. So the vertical resolution was like, so it's a stretching from the lower atmosphere we resolve more. So it's like 20 meters, 30 meters maybe at the lowest, but it's stretching towards the model top. The model top is 30 kilometers, and we have only like 50 levels in the vertical, or 40 levels in the vertical. So it's not a very high resolution model. I think that the operational model right now have like 100 levels. So it's like less than half or about half of that.
I see. Okay.
Yeah.
Another question is that, that they basically the time period for data simulation cycle to capture the storm. So what's kind of time period for data simulation at that case?
Time period?
Yeah.
So it's a
for data simulation cycle.
30-second cycle.
30 seconds.
Yeah, 30-second cycle, because we get the data every 30 seconds.
30 seconds.
Yeah, so it depends on what we would like to predict, because it depends on the chaotic time scale. So for individual convection, the chaotic time scale is quite short. We tested different time interval, the cycling interval, and 30 seconds works, and 1 minute it still works, but of course the 30 seconds is the best, and 1 minute is still okay, 2 minutes okay, 3 minutes bad. So 3 minutes is too slow.
Actually, a lot of data. Okay, and so basically another question is, you use the more than 1,000 some numbers, and so how the model, how the model outputs are stored and post procedures.
Yeah, that's a very good question. So for that experiment, we stored in disk space. So we wrote files, a lot of files of the model state.
Yeah.
And then DA just access those files to read in. So a lot of I/O. Because in that experiment, we didn't have the real-time requirement. And we, anyway, need to save the data for the post-analysis. So that's why we did that. But for the real-time system, that is bad because it's too slow.
So that
for
said,
the-
it is the bottleneck when you apply to the operational model.
yeah, that's right. But again, so we did a real-time experiment. At that time, we didn't save, or we save later, but we had all the data in the memory space. So what we needed was only the memory space access and communications among distributed memory space.
Okay.
So that was quite fast.
Okay. So another question is from Horado, and he said, so if you use a huge number of the sample members, and do you use the inflation?
That's a good question. Mostly, we don't need the inflation, but still, sometimes we need the inflation because the need for the inflation is not only by the ensemble size, but there are other imperfections like nonlinearity or chaotic dynamics. So those might affect well, it's different from the pure Kalman filter because the model is nonlinear. It's not just ensemble size. So sometimes it may be necessary, but most of the case, inflation is not necessary.
It's not necessary. And how, if you, again, for the 1 over the 1,000 assembles number, and how is the background? You got background assemble covariance.
So 1,000 ensemble members will produce the covariance matrix.
Yes.
Well, we run 10,000, then the rank will be 10,000 for covariance. That's still small compared with the degrees of freedom of the system.
Because the people may worry it's proximate to the full rank matrix.
So if you run 10,000 ensemble members, then if the system dimension is 10,000, we could have a full rank matrix. But weather system is much more than 10,000 degrees of freedom. So we have at least 1 million or sometimes 100 million degrees of freedom. Then we cannot afford running that large ensemble yet. So we don't have a full rank in that sense.
Okay. So another question from Horado. And for the OSSE, and which was the level of noise used?
Yeah, that's a good question. So in OSSE, we need to design the observation system. So we assume that, I showed 2 OSSE cases. One is the phase array. So the phase array, both are phase array. So one is a ground-based phase array. So the ground-based phase array, we have some good idea based on our existing research. So we assume the realistic noise that we deal with the real data. And the satellite-borne phase array, we assume something similar. So we just assume some noise level of the data. So that's something that we can change and see the impact or the sensitivity to those settings. But we just set some noise level.
For the
it's multiplicative, yeah.
Okay, multiple. For the CNN training process, and how many, how many was the time step you use, 3 volume data you used for training data set?
I'm not sure which one was this about. Sorry, I need to. So I had some examples of using. Yeah, I had some examples of using the CNN. One is this one. This one we use a CNN, and the other is this one. This one also uses CNN in the LSTM. I don't know which one. Just assume this one.
Can you clear which case you're thinking?
Okay, please go to the previous slide from this.
Previous one?
Yeah.
This one?
No, another one. When you talk a fusion, that's it.
This one?
No.
No.
No. It's stop. Not this one.
Go back.
Yeah. Go back.
Right.
This one?
No. Go back. You chose fusion, machine learning. That's
Yeah,
it.
this one.
This one. Okay.
This one.
Okay.
There is some delay, so that's why.
Mhm.
Yeah. Okay, I understand. Yeah, this one. This one. What was the question? Let's see. Yeah. So this volume data exists every 30 seconds, so that this phase array can observe the volume in 30 seconds. So the training data is the observation data, and all of these data, input data.
Purely observations.
Because you
input
show
here
a
is the
forecast or
model.
something, and then
Yeah,
I
the
think that's
model
your
is
combination with forecasting and observation.
Right.
Okay.
Everything has the same data format, and it's every 30-second volume of the radar reflectivity, or the rain amount, let's say. So this is a three-dimensional volume data
Right.
with radar reflectivity every 30 seconds.
Mhm. Any other questions from audio?
Okay, I think that it's
Thank
just
you
at the right time.
very much for your attending this.
Thank you very much.
Training. And so thank you again for the Professor Takamasa. And so I think really appreciate it's very late in your time, and thank you again.
Okay, thank you very much.
It's a wonderful talk, and
Thank you very much.
both of them, on the day 2, and you give the really detail of the INPE, the theory.